This is a very brief introduction to the background material on the history of science. There's a whole lot more than I am going to say here that could be said. This is not a substitute for a serious study of the history of science by any means. We're going to move very quickly. But there are a few things that everyone should know, and they will help us to understand some of the things that will come up later in our readings. We're going to start by looking backward at Aristotle, the dominant figure for more than a millennium and a half. Aristotle died in 322 BC. He was a philosopher and a scientist who gave us the idea of a centered cosmos, a world that has an absolute center. As it happens, the Earth is at that center. Some people have the misimpression that the center was a place of dignity and importance. Actually, the center is the least important place in the universe. The center is the bottom of the universe, the garbage can of the universe, if you will. So Aristotle's idea is that the Earth was at the center. The most base things, mere rocks, would fall toward the center of the universe, and that's where the Earth itself collected. But the more noble things were further away. So we should not confuse the idea of a centered universe with the idea of a special place for mankind. According to Aristotle, the Earth is spherical. Some people have the misimpression that in ancient times people thought the world was flat. This is not true. If you think about the geometry of a lunar eclipse, you'll realize that the shadow of the Earth is cast onto the disk of the moon, and that shadow always has the shape of an arc of a circle. The only three-dimensional shape that casts a circle as its shadow, no matter where you illuminate it, is a sphere. And for that reason and other reasons, Aristotle knew full well that the Earth was round. So that was not Columbus's discovery. People in the Middle Ages did not think that the Earth was flat. From Aristotle onward, every educated person had full reason to realize that the Earth is spherical. What Aristotle did hold that we have discarded is the idea that the Earth was unmoving at the center of the universe. That is sometimes called a geocentric, geostatic universe, with the Earth at the center and unmoving. So those terms, geocentric, Earth at the center, and geostatic, Earth unmoving, are terms that I may use again as I'm going through this. I wanted to introduce those before I moved on. Claudius Ptolemy flourished around the year AD 150. We know very little about him as a person, but he was an astronomer and mathematician, and he takes the Aristotelian view of a centered universe and fills it out in geometric detail. It's Ptolemy's construction that allows us to have a model of the solar system so good that we can make predictions years in advance with reasonable accuracy. If we want to know when an eclipse will take place, then we can tell this using Ptolemy's astronomy. At times and in places, it's a bit off, but on the whole, it's pretty accurate, and by far the most accurate thing that anyone had ever constructed. In order to make his detailed geometric model fit the data, Ptolemy had to abandon some of Aristotle's other ideas. For example, Aristotle had the idea that up in the heavens, where the stars and the planets are, everything moves with uniform circular motion. Everything moves at a constant rate around perfect circles. Ptolemy had to do some violence to that part of Aristotle. He also put together geometric models that would give you the data, but sometimes in ways that were incompatible with other parts of the model. So if you want to know what direction to look for the moon, Ptolemy will give you a geometric diagram and a computational device. If you want to know how large the moon will appear, you have to go to a completely different geometrical construction. The two constructions are not just different, they are incompatible. You cannot lay them down one on top of the other and make them line up. From Ptolemy's point of view, that's beside the point. The important thing is to be able to predict the phenomena, not to know how the real objects are moving through three-dimensional space. That's an interesting question, but in his main work, the Almagest, Ptolemy does not care about that particular point. And so throughout the work, there are incompatible geometric constructs, and the whole thing kind of looks cobbled together in a very awkward way. That will become important later on. One of the things that Ptolemy uses in order to get reasonable accuracy in his predictions is a series of what are called epicycles. These are small circles that ride around on larger circles, and sometimes small circles on epicycles. So we have epicycles, and these are basically fine-tuning devices that allow us to get the observational predictions to be a little bit more accurate. However, they're very ugly, and they clutter the system drastically. When people refer to epicycles in later work, usually it's a negative reference. Usually they use the term epicycles to mean needless complications. So Ptolemy's view, though it worked, seemed clumsy and awkward. We have to go back a little bit in time for the next fellow, best known by the name Lucretius. He was a Roman poet and the author of a work called De Rerum Natura, on the nature of things. Lucretius was an atomist. He believed that fundamentally there are only two kinds of things that are real. There are atoms and there is void or vacuum. Everything in nature can be explained in terms of atoms and the void. Lucretius' views were not compatible with Aristotle's views, and since Aristotle was the dominant thinker, Lucretius' atomism was a minor position throughout the history of science for quite some time. There are various reasons for this. One of them, however, is the association of atomism with atheism. Lucretius is very explicit that we don't need to talk about what the gods are doing. We can explain all of the phenomena of nature using atoms and the void. We can give atomic explanations for everything. So, for many centuries, there was a close association of atomism with atheism. And Lucretius, though he was not the first atomist, promoted it, and it became famous as in the method in which he had put it forward and in the work in which he had put it forward. So when we come into the Renaissance and Greek and Roman learning are recovered, Lucretius' work is going to be the standard work of atomism throughout the Renaissance, and that will color the way that people think of atomism. They will think of it as atheistical. Next up, we're going to jump forward in time. There are many other interesting figures in between, but we are going to come to Nicholas Copernicus. He was a Polish canon in the Catholic Church. If you look carefully at his dates, you'll notice that he died in 1543. He's almost an exact contemporary of Martin Luther. We'll talk more about Luther in a little while. Copernicus lived at a time when, despite all of the religious wars that were going on, Catholics and Protestants, even Lutherans, were often friends, and he had Lutheran friends with whom he would converse and correspond. His masterwork he wrote and published at the very end of his life. In fact, a copy of it was placed in his hands as he was on his deathbed, and he died a few hours later. It's De Revolutionibus Orbium Celestium, on the revolutions of the heavenly spheres. Copernicus replaces the geocentric model, the Earth-centered model of the solar system, with a heliocentric or sun-centered model. But he's a reluctant revolutionary. He's not doing this because he hates Aristotle. In fact, he's realized that Ptolemy has not been faithful to Aristotle because he's abandoned the idea of uniform circular motion. And so, to the greatest possible extent, Copernicus tries to go back to Aristotle's notion of how heavenly motion should go, and he abandons the idea of an Earth-centered, still Earth, geostatic cosmos because he wants to be faithful to other aspects of Aristotle's thought. Another thing that Copernicus does that's very important is he tries to construct a model that is physically realistic. He works very hard and largely successfully, trying to make geometric constructions that are compatible with one another, so that the predictions he makes from models which could be physically real. Some people have the misimpression that Copernicus got rid of epicycles. That is not true. For the accuracy of his predictions, he needed to have just as many epicycles as Ptolemy did, because he's working with perfect circles. And the only way to try to get the orbits to fit is to put circles on the circles and circles on circles on circles in order to generate orbits that fit the data that we have in our observation. So Copernicus is an important figure. He could be seen as inaugurating the scientific revolution, but he is not setting out to be a revolutionary. That's okay. Here's someone who did intend to be a revolutionary. Galileo Galilei was an Italian astronomer, a devout Catholic, though he got in some trouble with the Roman Catholic Church. In 1609, in the fall, he developed the first telescope that was capable of making decent astronomical observations, and in 1610, he published a book about it. These observations included observations of satellites of Jupiter, so that Jupiter was a center of motion, which meant that there was more than one center of motion in the universe. If you could have just one center of motion, as Ptolemy had tried to do, making the Earth the center of all motions, then there was a certain simplicity about your system. But if there were satellites going around Jupiter, then there must be at least two centers of motion, and at that point, you might as well go over to a sun-centered, heliocentric system if it would preserve the other data and be simpler in other ways. Galileo became an outspoken advocate for the Copernican view. In 1632, he wrote a book called Dialogue Concerning the Two Chief World Systems. This gets him in some trouble with the Roman Catholic Church. It's not so much that he says something that runs against sort of core Catholic doctrine, but he takes it upon himself to say that the Copernican view seems plausible in various ways, and because of the Protestant Reformation, the Catholic Church had declared that the Church alone, with its magisterium, its teaching ministry, was capable of interpreting Scripture. So if there are passages of Scripture that seem to say that the earth stands still, it is not the place of a layman like Galileo to read that as a metaphor. He probably could have gotten away with it, but he also put an argument which was the Pope's favorite argument into the mouth of one of the fools of the dialogue, Simplicio, who comes across as being rather a low-watt bulb, and someone drew the Pope's attention to this, and so Galileo actually probably could have gotten through the Inquisition without much trouble. They wanted to let him go with a sort of simple plea bargain agreement, but the Pope declared that he must be threatened with torture and made to recant his views publicly. The Inquisition did all that it could to make that sentence light for Galileo. 3 members of the 10-member Board of Inquisition would not even sign the condemnation. They immediately converted his arrest to house arrest, and then converted that to house arrest at his own home, so he was allowed to go back and live in his own villa and receive guests there. He received the English poet John Milton there. Milton looked through his telescope. So he spent the last years of his life there. Galileo died in 1642, and that's a date that we will want to keep in mind because there's a nice coincidence associated with it. Before we do that, though, we need to look at Robert Boyle. Robert Boyle was a young son of an Irish nobleman. He was not the oldest son, so he didn't get the family title, but he was an eminent experimental scientist. He worked with vacuums and with the atomic hypothesis, extending that to many natural phenomena. Boyle was also a devout Christian, and so in some ways it's to Boyle that we owe the baptism of atomism, the bringing of atomism out from under the shadow of atheism and saying, no, a devout Christian can use the atomic hypotheses just fine, and there's nothing intrinsically atheistical about them. Boyle wrote a work called The Christian Virtuoso. I will talk about that briefly a little bit later. And when he died, in his will, he established an endowment for the Boyle Lectures for the Defense of Christianity against its adversaries. As we're reading works in the Deist controversy, we'll find that many of the books that we are reading are lectures originally delivered as Boyle lectures. So the Boyle lectureship really got the public defense of Christianity rolling and provided some support, financial support for it. Next up, Isaac Newton. I said 1642 was an interesting date. On the old calendar, which was still in use in England at the time, Isaac Newton was born on Christmas Day, 1642. On the new calendar, it would be early in January of 1643, but the English were old-fashioned and they stuck to their old calendar for a long time. Newton was, by pretty much everyone's estimate, the greatest genius in the history of science. His mathematical principles of natural philosophy, commonly known as the Principia Mathematica, was an attempt to give a single mathematically rigorous system whereby, in terms of a few general laws, we could explain all natural phenomena, to which there are no natural exceptions. Physical phenomena are explained in terms of those laws, like the law of gravity or the law of action and reaction. Newton picked up pieces of what other people had been doing in the history of science. Descartes, Kepler, Galileo himself. He chose just the right elements from these other thinkers and he synthesized them. He put them together. And for that reason, what Newton achieved is sometimes called the Newtonian synthesis. By the early 18th century, the 1700s, right smack in the middle of the period we're going to be reading, Newton's reputation was so great that there was no one on earth with a higher reputation as a scientist. Alexander Pope wrote of him, "Nature and nature's laws lay hid in night. God said, 'Let Newton be,' and all was light." It was also said of Newton that he was the most fortunate man who had ever lived because there was only one universe, and to Newton belonged the honor of having discovered its laws. Newton, however, was devoutly religious and did not believe that the universe was by itself simply an autonomous clockwork. He believed that it had been created by God, and he believed that God intervened in it with miracles and prophecy. And in fact, many people don't know this, but Newton wrote voluminously. He almost never threw away a piece of paper. So we have a tremendous backlog of Newton's papers. He wrote more about the interpretation of prophecy in Scripture than he did about mathematical physics. He was intensely interested in this. When the first Boyle lecturer, Richard Bentley, wanted to use some of Newton's work as part of his argument for the existence of God, Newton wrote to him and said, "Sir, when I wrote my treatise about our system, I had an eye upon such principles as might work with considering men for the belief of a deity. Nothing can rejoice me more than to find it useful for that purpose." So here's Newton explicitly endorsing the use of his physical work as promoting belief in God. This became something of an embarrassment in free-thinking circles because everyone acknowledged that Newton was a great genius. But Edmund Halley, the discoverer of Halley's Comet, as we would now call it, was a freethinker. And there's a funny story of one occasion on which Newton and Halley were both present, and Halley made some slighting remark about Christianity. Newton is said to have turned to him and fixed him with his eye and said, "I have looked into these things. You have not." And that pretty much ended the conversation. Nobody replied to Isaac Newton when he was in that mood. There are many interesting and funny stories I could tell about Isaac Newton, but I will bypass them in the name of getting on. So just briefly, why does science matter in the deist controversy? One of the criticisms of the idea of a miracle is that miracles are violations of the laws of nature. We'll see this coming up in Hume. Because the cultural prestige of science was very great in the early 18th century, and of Newton in particular, we need to watch the way that people handle references to the laws of nature. Both sides will claim that they are being faithful to the idea of laws of nature, but they will mean different things by that. So watch for that. Keep your eye open for that. The idea of a clockwork universe raises questions, both about a designer, a clockmaker. William Paley talks about this in his Natural Theology, and about the self-sufficiency of nature. So Bolingbroke and Alexander Pope and other deists would argue that God does not work by special interventions. There are no miracles. God sets up general laws, and then that's the way the universe runs. Finally, there's the point that to identify something as a miracle, one needs to know what nature can do by itself. If you don't know that, then rare natural events may be misidentified. So Boyle, in The Christian Virtuoso, argues that the best person to study the question of miracles is the devout Christian who has also mastered physical science, because that's the person who will best know what nature can and cannot do on its own. So those are some of the principal things that we need to keep in mind from the history of science. I'm going to pause now, and I assume some of you will have questions.